I'm Alan Fryar from the Department of Earth and Environmental Sciences at the University of Kentucky, and I'm presenting work that was done in collaboration with my former PhD student Ganesh Tripathi on spatial and temporal variability in groundwater discharge and contaminant fluxes along Little Bayou Creek downstream of the Paducah gaseous diffusion plant. In terms of background, Little Bayou Creek is a perennial first-order stream, meaning that it has no tributaries that flow all the time in the Ohio River floodplain, and it's located in the Gulf Coastal Plain region of far western Kentucky. In a previous study, which was done in conjunction with former PhD student Danita Lesage from 1999 through 2002, and with a former master's student, Obajit Mukherjee, we looked at a 300-meter long reach or segment of the stream at the head of part of Little Bayou Creek that had been channelized around ash ponds at the TVA's Shawnee steam plant. And we found that stream flow increases and springs occur along the head of that channelized reach, which was about 300 meters long. We found that springs appear to coincide with heterogeneities in the clayey metropolis formation, which is a relatively low permeability confining unit overlying the regional gravel aquifer at the site, which is known to be contaminated. And we found, or inferred, that channelization may have promoted groundwater discharge, in particular along this 300-meter long segment of the stream. The springs that occur along this segment appear to discharge from the northwest plume that originates at the gaseous diffusion plant. And we found concentrations of the groundwater contaminant trichloroethylene, which is a priority pollutant and suspected carcinogen, up to 450 micrograms per liter, as compared to the EPA's Safe Drinking Water Act standard maximum contaminant limit of 5 micrograms per liter. We also found concentrations of the radionuclide technetium-99 up to 461 picocuries per liter. And technetium-99 is an exotic contaminant that occurs at concentrations less than the site-specific contaminant level, but high enough that we can trace it as originating from the gaseous diffusion plant. This is a map, a generalized map of the study area showing hydraulic heads or groundwater levels in wells penetrating the aquifer as of September 1997. And this map is from a paper published by Danita Lesage and others in Journal of Hydrology in 2008. And what you see here is the gaseous diffusion plant. This is actually plant north. True north is oriented this way. You can see Little Bayou Creek here. These are the equipotential lines, or the lines of equivalent hydraulic head, and you can see that they decrease from 100 to 99 to 98 and so forth toward the Ohio River, which is at about 89 meters above sea level at this time. You can see here this dashed line, which is the trace of Little Bayou Creek before it was channelized beginning in the early 1950s around the TVA ash pond. And you can see monitoring sites downstream, prefixed LBC, of this 300-meter channelized reach. And all of these dark dots here, prefixed EB for East Bank, WB for West Bank, or MS for midstream, represent springs that were mapped along this reach. With the same base map from another companion paper by Lesage et al. In Journal of Hydrology in 2008, you can see a generalized overlay of the northeast and northwest contaminant plumes, and the stippled pattern here represents TCE concentrations greater than the maximum contaminant level of 5 micrograms per liter, and the cross-hatched pattern represents technetium-99 concentrations, again in groundwater, above a detection limit of about 25 picocuries per liter. And so you can see these plumes overlap. The northwest plume originates from the northwest part of the plant, the northeast plume from the northeast part of the plant, and these plumes pass underneath, in particular the technetium-99 plume and the northwest TCE plume, this reach of Little Bayou Creek where the springs are. In the study currently with Tripathi, between October 2010 and February 2012, funded through KRCEE, We looked at base flow of the creek, that is, flow when there had been no significant precipitation for at least 24 hours preceding, at about 3 to 5 month intervals, so roughly quarterly to, in effect, seasonally. And we also did some continuous monitoring of hydraulic heads in adjoining monitoring wells and of groundwater temperature in some of the springs. And we looked at different spatial scales, in addition to different monitoring intervals. We started out with individual springs, which would be at the scale of about 1 meter, to clusters of springs, which occurred at scales of about 10 meters, to the sub-reach to reach scale on the order of about 100 meters. And then temporally, I mentioned that we were looking at seasonal variability. In some instances, we actually looked at diurnal, that is, daily variability. We did this over a period of more than a year, and we compared it with the work done previously by Lesage and others, so we could actually look at timescales from daily to decadal. In terms of our methods, first we had hydraulic methods where we were monitoring heads in individual wells and measuring flow of individual springs, gauging at increments of tens of meters along the 300-meter reach of the creek. Transects across the creek were gauged. And finally, over the entire 300-meter reach, we did dye dilution tests where we injected fluorescent rhodamine dye and looked at its movement down the creek. We did thermal monitoring. We monitored temperature in springs under the presumption that groundwater temperature is relatively constant once you get below a depth of a few meters below land surface. And it is roughly equivalent to the annual average air temperature, which in this area is about 15 degrees Celsius, plus or minus a degree. We also did seasonal temperature probing on a grid, recognizing that if groundwater temperatures are relatively constant, around 15 degrees Celsius, but if air temperatures clearly fluctuate, such that they're coldest in winter and hottest in summer, then we can map groundwater temperatures coming up into the stream in the summer and in the winter and pinpoint thermal anomalies, which indicate areas of groundwater inflow. And all of these techniques that I'm talking about are techniques that have been applied elsewhere. They weren't necessarily invented by us. We also use a newer technique called distributed temperature sensing, which involves stringing fiber optic cable along a reach of the creek, firing a laser light down the fiber optic cable and looking at the attenuation of the light signal moving down the fiber optic cable, which is a function of temperature. And this kind of backstopped the seasonal temperature probing and the monitoring of temperature in springs. And finally, chemically, which after all was sort of the motivation for this study in terms of contaminant fate, we sampled selected springs and the stream at various locations for volatile organic compounds, including TCE, for technetium-99, and for dissolved oxygen, because studies have shown that trichloroethylene is more likely to degrade under anaerobic conditions, that is, in the absence of dissolved oxygen. Therefore, where dissolved oxygen is present, that may mean that TCE degradation is less likely or at least less rapid. And finally, we integrated the data by mapping discharge sites and calculating fluxes. So note that the orientation here is different. This is the study reach zoomed in, but north is to the left. And so we refer to these actually sub-reaches as reach 1, reach 2, reach 3, and the solid lines across the creek represent temperature probe transects for summer and winter, January and August, and the dashed lines represent gauging transects upstream and downstream of springs. So the springs are noted with the little blue squares. You can see, for example, this is spring WB 1.5. This is gauging transect WB 1.5D, which is downstream of the spring, and WB 1.5U, which is upstream of the spring. This is a photograph from August 2002 of my former graduate student Abhijit Mukherjee gauging at the downstream end of the reach. Gauging by weighting using a current meter along a transect across the creek marked by a measuring tape. This is the same location in July 2012, so the same time of year a decade later, and this is after a fairly pronounced drought, and you can see that it was dry enough, the flow was low enough in the creek that there was actually vegetation growing on the sandbars. And this is a view from the same site in January 2011, and you can see, in addition to the foliage being off the trees, that the creek was actually iced over. So clearly, the flow of the creek and the surface temperature regime varies seasonally. In terms of our results, physical results first, what we found is that hydraulic head in a pair of stream bank wells, monitoring well nest at the downstream end of this 300-meter study reach, varied over a 5-month period of continuous monitoring with rainfall. Rainfall at the Paducah Airport is shown here in green on the left axis in units of centimeters, and hydraulic head in meters above mean sea level is shown at right. And what you can see over this period from late September of 2011 until late February of 2012, which captures from the dry season into the wet season, is fluctuations that correspond with individual rainstorms, these peaks. But what you also see is that at a more gross level, the head tracks the Ohio River stage. So this is Ohio stage at Metropolis, Illinois, a few kilometers upstream just opposite Paducah. And you can see again low stage here and increasing as you move into December. And this is kind of a characteristic response. There are fluctuations, but basically water level in this pool along the Ohio River tends to be relatively low in late summer and autumn and increases in winter and early spring. So the groundwater flow paths, if you remember the map that I showed of the equipotential contours and the contaminant plume, groundwater flow paths vary seasonally as well, responding to individual storms, but also at a longer time scale to the fluctuation in the Ohio River level. We found that discharge Q, the flow rate, here given in liters per second, of individual springs varies seasonally, but also with piping, which is the process by which groundwater sapping erodes away the sediment from the bank or in the stream bed. And so these springs, instead of being labeled WB or EB or MS, are just labeled actually with reference to distance to a common point, the farthest downstream site that we monitored at the edge of the TVA ash pond. So 1075 to 1485, this is about 410 meters. And this is from June 1999 to May 2001, the work that Nita Lesage did for her doctorate. And what you can see is that typically discharge values, spring flow rates, would be higher in the springtime, in June, for example, or May, and would be lower in September, which is consistent with water levels being lower in the wells, water levels being low in the river. It's the relatively dry season. For some of these springs, they rebounded from year to year. Other springs did not because, in effect, the piping, the erosion, caused the bank to cave in. So some of the springs actually migrated. And one of the questions in this study was, how persistent were these springs over a period of a decade? So you can see here, this is spring WB3, the largest spring, one of the farthest upstream springs. This is a folding rule, so this is about 4 feet or about 1.3 meters across the orifice of this spring in August 2002. We returned in October 2010. 8 years and a few months later, you can see that a lot of this had eroded away, some of it no doubt by surface runoff, some of it by stream flow, but probably a lot of it just by the action of piping carrying the sediment with groundwater discharge away from the site. This diagram is a little bit complicated, bear with me. This is a plot of stream discharge, and it's in units of volume per time again, but in this case, to simplify things, we've got it in cubic meters per minute rather than liters per second. And this is normalized, so it's plotted against days of the year, obviously 0 to 365, representing different times at which we were monitoring during the different studies. So this blue diamond is for gauging location EB2D in the initial study from 1999 to 2001, so the farthest downstream gauging location. Farthest upstream is WB3U, next to the large spring I showed in the previous slide, from 1999 actually to 2003. And then again, EB2D as the green triangle from 2010 to 2012, and again the farthest downstream, the farthest upstream site, WB3U, from 2010 to 2012. And so what you want to look for here is, in each instance, EB2D being higher than WB3U. And in most cases, except for this instance in early January, you can see that yes, in fact, the blue diamond is above the red square, or the green triangle is above the blue X, pretty much consistently throughout the year. Again, indicating that as you move downstream, you pick up flow, and that flow is coming in from the springs. We checked this also by injecting fluorescent rhodamine dye in a dye dilution test over 5 periods, I believe, from 2011 to 2012. So we did this seasonally. And this is a conceptual diagram from a U.S. Geological Survey publication by Winter and others, Groundwater and Surface Water, a single resource. And this shows several phenomena that are potentially relevant here. One is that where you have a small stream with pools and riffles, that is sandy and gravelly beds like Little Bayou Creek, not only do you have water flowing in the stream and groundwater flowing toward the stream, but you can actually have water flowing through the bed and the banks in what's called the hyporheic zone, the groundwater surface water mixing zone. And so you can see that through the banks here, through the bed here. What can also happen when the water level rises in a stream is that temporarily you can get something called bank storage, which is that water moves laterally away perpendicular to the stream into the banks. And then when the water level drops later, this temporarily stored water comes back out again. So that was one of the things we were looking at also. To what extent was water moving within the bed and the banks, not just from the subsurface into the stream or within the stream? And what we found is that if you look at net exchange, which is in effect the water that is inferred to move through the bank from tracer tests like the dye injection, from gauging upstream and downstream, and you look at inflow, which is the net amount of water coming in along this segment of the stream, that the two values in January and June were essentially identical. In October and February, there was a little bit more net exchange, so there was more water that had left the system and had not come back into the creek along the segment that we were monitoring. But in general, and this is in units of velocity in meters per day, the amount of water that flowed into the creek from groundwater did not stay within the bed or the banks. It moved back out into the creek, although it may have meandered en route. We also looked at calculating an annual average groundwater flux various ways, one using Darcy's law, which is the standard equation for describing groundwater flow, the velocity area method, which refers to gauging at various segments along the stream and then dividing the net change in discharge by the area of the bed of the stream, by dye dilution, and then by a combined method developed by Harvey and Wagner. And you can see that all of these values of net flux or inflow are within the order of about 1.1 to 1.6 meters per day. So they're all pretty comparable to each other by different methods, which again suggests that there's not a lot of water being lost or stored for an extended period of time in the banks or in the bed. It moves from groundwater into the stream. We also used temperature loggers. This is a brand name, Hobo, manufactured by Onset Corporation. And we installed these in September of 2011 and monitored them until January of 2012. And what you can see here is there's some fluctuation, but in general, the temperature in the spring is right around 15 degrees Celsius, relatively constant, which is what we expected. Now, these spikes probably correspond to individual storms, and we think what happened after late November 2011 is that because these things tend to be buoyant, that it was actually yanked out from below the water level, and so all of a sudden you're seeing temperatures that are a lot more variable, at least for about a month or so, that may represent it being out of the water. In terms of the stream bed temperature probing, we used a stainless steel thermometer with a point 4 feet long, of the type that's actually used for measuring the internal temperature of meat carcasses at packing plants. And this is a technique developed by Susan Hendricks and David White at Murray State University, actually. And we simply pushed this into the stream bed as far as we could go on a grid. Basically, every 10 meters or so along the stream, we would do the transect, and then we would probe, every 10 feet, and then we would probe at 3-foot intervals across the stream. This is the temperature in degrees Celsius. This is in January 2011. This is 12 degrees Celsius, and that's relatively warm, which again is consistent with groundwater flowing into the bed of the creek. The fact that the temperature is a little bit cooler than what we had shown for the Hobo is probably indicative of the fact that there was some thermal exchange between the groundwater and the stream water, which was a lot colder. This is a plot that compiles for probing in January 2011 and probing in August 2011, all of our temperature measurements along the grid, if you will, along the sets of transects along the 300-meter study reach of the creek. This is in depth, feet below the surface of the creek. And what you can see here is there is a rough trend. Again, we're taking data that are three-dimensional and crunching them down, in effect, to a one-dimensional plot. But temperature tends to increase with increasing depth. And in August, temperature tends to decrease with decreasing depth, and these values move asymptotically toward about 15 degrees Celsius, which is roughly what the average groundwater temperature is. And this is consistent with a conceptual streambed profile. This is from a report by Jim Constance and others, the U.S. Geological Survey in 2008. Again, you can see where you have an upward flux, you have groundwater temperature decreasing as you get closer to the surface, or increasing with greater depth, conversely, in the winter. And in the summer, you have the temperature relatively cool and increasing as you get closer to the surface. So we see the same kind of envelope as one would expect for what's called a gaining reach of the stream, where you have an upward flux, where groundwater is moving into the stream. This is a color-coded map of temperature, and it's plotted with stream bed depth. What you can see here is this is August 2002, August 2011, January 2011, and for purposes of consistency, even though it may seem a bit counterintuitive, for January, the hot color here, the orange, represents temperatures of about 14 to 16 Celsius. For August, we also use the hot color to represent temperatures of 14 to 16 Celsius. So in fact, in summer, in August, as you move to the cooler temperatures, you're actually getting warmer. In January, as you move to the cooler temperatures, you are in fact getting cooler. So this may be a bit counterintuitive, but we did this so we could plot data from different seasons on the same scale. And what you can see is, if you focus on the red spots, over a period of 9 years, and as well a period of 7 months, you can see spatial persistence of these springs at scales of a few meters. So this is distance in meters along the reach here. And I apologize, I've been doing the classic geologic thing and moving back and forth between English and metric units. So remember that 1 foot is 0.0348 meters. And here, MS1E, MS1W, EB5, EB4, EB2, WB1, WB0.5, MS2, WB2, WB3 represent the mapped locations of springs. And so where we saw springs in our original study, we tended to see springs. Some had disappeared, some others had emerged, but they basically were located in the same area. This is a plot of temperature probing along a subreach, reach 2, from 95 to 145 meters upstream along this 300-meter segment. And this represents the DTS, or distributed temperature sensing. And again, the scales are reversed here, so bear with me. The hottest colors for temperature probing, this is from August 2011, are shown, the hottest temperatures are shown in the coolest colors. So 27C, the warmest temperature, is dark blue, 15C is red. And it's inverted, and note also that the scales are a little bit different. This is 23 here is the highest temperature in the hottest color, and 8 here is the lowest temperature in the coolest color. So this is a bit of an, maybe not apples and oranges, but lemons and limes comparison. what I want you to note is that where we see the anomalies from temperature probing, we also see relatively low temperature anomalies from the fiber optic method. So by two different methods, at least qualitatively or semi-quantitatively, we can confirm that there appears to be groundwater inflow at discrete points along the creek. Finally, in terms of the chemical results and contaminants, this is a cross plot of TCE, trichloroethylene, versus technetium-99. And the reason we have technetium-99 on the x-axis is that technetium-99 is thought to be relatively chemically conservative. Over long enough time scales, perhaps 300,000 years, it will decay through one half-life. But over the time scales we're looking at, years to a decade, technetium-99 is relatively chemically unreactive. TCE, as I mentioned, under anaerobic conditions, depending upon how anaerobic they are, can be degraded, biodegraded to so-called daughter products, such as the dichloroethene isomers and vinyl chloride and potentially ethene. What you see here is a relatively tight linear relationship between TCE and technetium concentrations. The fact that TCE is covarying linearly with technetium suggests that whatever is happening to the technetium happens to the TCE, and therefore the TCE in the springs is also, in effect, unreactive, that it's not breaking down. Note the scale here. TCE concentrations, micrograms per liter, 0 to 600. Technetium-99 concentrations, picocuries per liter, which is an indication of decay, 0 to 600. Here we have rescaled, this is for 2011-2012 data, 0 to 200, 0 to 200. Note that this relationship is still linear, but the slope has changed. In other words, technetium-99 concentrations and TCE concentrations have decreased over the intervening decade in the springs, but the technetium-99 concentrations have decreased more than the TCE concentrations have, which begs the question, why? Well, these are data actually from the site operator and their contractors showing concentrations either in micrograms per liter, the open diamonds for TCE, or picocuries per liter, the filled diamonds for technetium, in the intervening period, overlapping the two studies from December 1999 to April 2012. And what you see for TCE is that concentrations kind of bounce around, but particularly after 2006 tend to decrease, whereas technetium-99, beginning around 2000, decreases pretty substantially. What we think is happening at the scale of individual springs along this 300-meter segment, so 10 meters, let's say, 1 to 10 meters, is that we've got some stream water that seeps into the bed, comes back up, and we have some diffuse groundwater discharge, but in general, because the bed and the banks tend to have a veneer of a veneer of sand and gravel over clay, and the clay is relatively low permeability, that focused groundwater discharge is occurring at these springs where you have, in effect, joints in the clay or cracks in the clay. That's at the scale of individual springs. Along the longer channelized segment, again, this is from Lesage et al., one of the 2008 papers in Journal of Hydrology, you can see that we have the focused groundwater inflow here. Some of the TCE and technetium actually passes with the groundwater under the stream. Downstream of where the springs are, there is some volatilization of the TCE, and we get some diffuse uncontaminated groundwater coming in that actually dilutes the TCE and technetium concentrations further. Finally, in terms of looking at the mass fluxes, if you multiply the net change in stream flow from the upstream to the downstream end of that 300-meter segment, so that's going to be in volume per time, say liters per second, and you multiply that by the concentration of technetium or TCE, in this case TCE, which is in units of mass per volume times volume per time gives you mass per time. So you have a mass flux here in micrograms per second in this case. And what I want to point out here are more the patterns than the absolute concentrations. You can see that the mass flux was highest in June 1999 and May 2000 and May 2001, lower in September 1999, January and October 2000 and January 2001. So we definitely see seasonality in terms of the contaminant concentrations that are coming in. You have both the greatest groundwater inflow and the highest concentrations during the wet season in our original study. In the follow-up study that I'm describing now, what we actually see is the highest concentrations in October 2011 and February 2012. Not sure why we see this shift, but what you can see is the highest concentrations we see here are still lower than the highest concentrations we saw in the previous study. So again, there has been a reduction in the contaminant mass coming into the creek over the intervening decade. So to summarize the results, in terms of hydraulics, the hydraulic gradient, the direction of groundwater flow, is relatively uniform upward in the pair of monitoring wells at the downstream end of the study reach. That's consistent with groundwater flowing into the creek. We find that the spring flow fluctuates seasonally with the position of the water table. Water table's higher during wet times of year, lower during dry times of year, but it also fluctuates with geomorphic changes, such as collapse of the bank or infilling with sediment. The locations of some of the springs have persisted for more than a decade, and the stream flow tends to be greatest in the late winter to spring. Lastly, the stream flow tends to increase from the upstream to the downstream end of the reach, which is consistent with flow coming in from the springs. In terms of the thermal results, these complement the physical results. Temperatures in springs can fluctuate diurnally, but they're relatively constant, around 15 degrees Celsius. When we aggregated our data, if you remember the plots with the asymptotic curves, at the sub-reach to reach scale, we found that the temperature varies with the probe depth, becomes warmer with depth in winter, cooler with depth in summer, but again, you're approaching a constant value. The temperature probing tends to corroborate the spring locations and suggests that the area of focused discharge is only a small part of the entire study reach, only about 3 to 6% of that 300 meter long by perhaps 5 to 10 meter wide stream segment. And some of the thermal anomalies that we delineated by manual temperature probing coincide with those inferred from the distributed temperature sensing over a period of about a week using fiber optics. In terms of the chemical results, again, referring to the data from the site contractor, the technetium concentrations in the springs have decreased more over the intervening decade than the TCE concentrations. And to our surprise, the TCE mass fluxes from groundwater to the stream decreased in spring and summer, but not in fall and winter, which may have some implications for changing contributions of contaminants from different springs along the reach, because we know that the concentrations varied with distance along the stream. We didn't see dissolved oxygen low enough to be anoxic in the springs, and we did not see the inferred daughter products of reductive dechlorination of TCE, such as the dichlorethanes. So that indicates that there wasn't reductive biodegradation going on intrinsically. Now, there have been some studies that will be talked about by some of the other researchers on this project, looking at the possibility for very slow aerobic biodegradation within the aquifer. And we conclude finally that the decrease in the contaminant concentrations that we saw is probably a result of pumping extraction wells in the Northwest Plume pump and treat system. Thank you very much.